Hi, my name is Ravishankar, and I'm from Idaho Falls, working in the Center of Advanced Energy Studies. I'm working for Professor Milos Manek on computational intelligence, and this is my course project called DC Motor Neural Controller. The objectives of the project were to build a DC motor control circuit and control this circuit via a PC or a laptop using serial communication and we to build a GUI, a graphical user interface that sends the control commands to the DC motor circuit, as well as display real-time RPM sensor data, and then acquire data from the GUI to train the neural controller, and then use the neural controller to control the DC motor's RPM at the given set point. The DC motor circuit was built using Microchip's PIC18F2331 microcontroller. A PIC is in full form a programmable interrupt controller. We can do all kinds of it's a microcontroller mainly used by hobbyists and industrialists. It's a basic microcontroller where you can create control circuits, and I used Allegro Microsystems AS3953SBT full bridge PWM driver. It's a H-bridge driver that drives the DC motor using PWM signals. PWM is pulse width modulation. The DC motor used was a product from Hanseng Corporation, and the optical encoder that senses the RPM was the US Digital QME01 optical encoder. The serial communication, the microchip PIC18 has EUSART pins that enable serial communication with the device. EUSART is in full form is Enhanced Universal Synchronous Asynchronous Receiver Transmitter, and you can do normal synchronous serial communication using a USB port to the device through these pins. And for this project, the serial baud rate of 9600 bits per second was selected. I constructed a few control commands to control the circuit as well as receive RPM data. From the PC to the DC motor circuit, a simple command string that contained the PWM duty cycle and the phase was sent, and then from the DC motor to the PC, a string that contained a start byte, a timer high byte, timer low byte, and a checksum byte were sent. The timer high byte and timer low byte encode the number of microseconds it took to the pulse of the pulse width of the RPM signal, data signal, and that's what we sent. And then I converted this raw data into RPM using a formula I'll show you later. Example commands from the PC to DC motor. Here's like the PWM 5, and that's the phase that gives you 5% PWM duty cycle ratio and clockwise rotation of the motor. So if it's 1, it is counterclockwise. So I can put 20 here for the PWM signal, and I'll get 20% duty cycle from the PIC microcontroller. And then from the DC motor, I send a control string like this, where 128 is a start byte, 0 is a timer high byte, 205 is a timer low byte, and 179 is a checksum that adds all these numbers to a value that is divisible by 256. And then once the PC detects this control string structure, it uses this formula to calculate the RPM. So that is 60 divided by 120. 120 is the number of spokes in the optical encoder, and then this is the conversion of the word into a 16-bit value, and then this is multiplied by 0.5 into 10 to the power minus 6, and that comes from the the internal clock in the PIC that actually does this timer updation. So it updates at the rate of 2 megahertz, and that's the time period that is equal to 2 megahertz there. And so I plug in this formula and I get the RPM, and I display it onto the graphical user interface. A simple GUI was built in MATLAB using the guide tool. It's a very simple GUI software tool that you can build simple GUIs in it without much coding on it. Here's a sample of the GUI window I created using the tool, sorry. And once the GUI was built, I was able to run the DC motor and send commands to it and receive data from it and display it onto the GUI. And then, as you can see in the previous slide, I have a log training data button. I use that button to log training data from the DC motor. What it does is, once I click the button, it begins to vary the PWM duty cycle that is sent to the DC motor, starting from 60% to 0% and all the way back. Why 60%? Because that is because of the H-bit converter. It has a active low enabled signal that actually receives the PWM signal, and then when I give it a 0% duty cycle signal, that means it's the voltage input to it is the ground voltage, that is 0 volts, and that's when it starts running at full speed. And if I keep varying this duty cycle from 0 all the way down to 60%, at 60% it stops, so that the motor does not move at all, it does not rotate at all. So, and it had some nonlinear characteristics because of the H-bit converter. So if I vary from 60 to 0%, I get a different response when I move from 0 to 60%. So I try to log in that information and train my data, and all data that is acquired from the training data, all data was stored into the motor data 0.mat file. That's a MATLAB specific file which MATLAB can only read, and I use that format to log in training data, and then from this data I trained a neural controller. So now we can move into the neural controller demonstration. So this is the DC motor graphical user interface I created. I called it the DC motor HMI. So you can see that it displays the RPM sensor data in this window here, the PWM duty cycle percentage control input in this window, and the phase clockwise or counterclockwise in this window. So let's connect the motor and run it. So as soon as I run it, it tries to meet this RPM, the set RPM. There's some error in the set RPM and the actual RPM because of the neural controller. It's just an approximate, not an accurate thing. So let's try a different RPM. So here you can see that it will slowly move towards the actual set point RPM. for some RPMs it does exact match close to it, and for some it does not, and that's because of the neural network that is designed for controlling. Neural networks have basically function approximators, and they don't give you exact functions. So you can see here that the RPM has already reached somewhere close to the set point. It's around 4,900, which is pretty okay. Let's try a different RPM, 4,000 probably. So you can see that the speed has reduced and the RPM is trying to closely come towards 4,000. So you can see here, this is the PWM duty cycle percentage that brings the RPM to this value. As you can see, there's a lot of noise in the RPM data that is being displayed. I didn't have much time to filter the data coming from the microcontroller. Let's try rotating the motor in the counterclockwise direction. All I have to do is click this button and it will begin to turn the motor the other way around, and it still tries to match the set RPM quite closely, although there's some error. And you can see that this is the PWM control input required. So let's see how the logging of the training data was done. All I had to do was, I created this button for that purpose, and then we'll see now what happens during the logging. So let's click this button. So as you can see here, it starts from 60, and then it will slowly increase the RPM within the range. You can see right now it's slowly increasing the RPM, and it's logging data simultaneously as it's changing the PWM cycle, duty cycle. Usually if it's at 60, the motor stops. From what you have seen here is that there was still some movement, just some nonlinearities with this circuit. You can see here, as it is logging training data, there's still a lot of noise in the data. There was a lot of noise in the data, and so before I did the training process, I did some filtering on the data. So I did filtering during the training, on the training data, not from the data, not on the transmission data. The thing is, neural networks require some form of clean signal, not exactly clean, to train a neural controller. So it went from 60 to 0, and now it's going back to 60. So now you can see, so the logging of the training data was done, and then after it trained the data, after it logged the data, it's trying to meet this RPM. So that's one indication that the training data was already logged. That's pretty much what I have for the GUI. You can see it's slowly increasing to meet this set point. And we are almost there. So that concludes my presentation. As part of conclusion, I built an example SCADA system for a DC motor circuit. The system was able to send control commands as well as acquire data from it, and from the acquired data I was able to train a neural controller to eventually control the DC motor circuit. Thank you.